I want to say a few things up front here before we get started. I find amateur radio is interesting from the standpoint that it brings together many different sciences. We've got electronics, both analog and newer digital electronics. We've got antennas, antenna theory, which can be a lifetime study in itself. We've got transmission line theory, which there's more to that than just a cable or a pair of wires that connect your transmitter to your antenna. We've got radio propagation, the mysteries of everything that goes on between our antennas. That body of knowledge has grown tremendously in the years that I've been a ham. We've married computers and software and the internet to this hobby, and I imagine we're going to start seeing artificial intelligence showing up here. So we bring together many different fields of different sciences to create this fantastic experience that we all get to enjoy called radio. I'm going to be approaching HF radio from the viewpoint of somebody that spent my life operating on Morse code, CW, and on voice single sideband, and in my early days AM. And so everything I'm going to cover here will apply across the board pretty much regardless of what mode you operate, but it'll be coming from the standpoint of a guy that works CW and sideband. If we get into mentioning FT8, Jim is the expert. Jim is the expert on FT8. If he wants to throw a little something in along the way, he can, but I don't have that experience. But the hobby is so diverse. I mean, we've got people that get into the hobby that know nothing about electronics, not interested in science. They just want to experience making contacts, turning on the radio, and having a good time with the radio, all the way to the other extreme where we've got some recognized experts in the ham radio fraternity that are some of the finest engineering minds on the planet, in my opinion. And I know I follow some of them on the internet, and I learn a lot from them. Where I fit into that schedule is more, I'm a science guy, but I'm nowhere up there on the top end of these really elite guys that have this stuff all mastered. But I've spent my life trying to learn and understand what makes this stuff all work. Now, just as I like to tell stories, and I'm going to be sharing history with you, I have a good buddy of 50-some years in Illinois. His neighbor is a ham. He's a retired school teacher. He's a fascinating person. He's a big-time DXer, spends all his time on the radio working all the countries on all the bands. But he absolutely refuses to learn anything about anything. He doesn't want to know anything about electronics, propagation. He just wants to turn that radio on and have fun. The hobby has room for everybody. Which end of the spectrum you want to go to, that's entirely up to you. I'm going to be coming to you from the standpoint of a CW guy and a single sideband guy. So that's one other thing. This is going to take 2 sessions to get through this whole thing. And so I'd like to think I can get the first part done, and then we'll do part 2, standing wave ratio. But the thing that I decided last night that's the most important to me this morning is to take our time to work through this step by step, and we'll go till, if we get close to lunchtime, we'll just knock it off, make note of where we were, and we'll continue in the next session. So I don't want to rush it. I want to take time to do things right, or whatever. Okay. I'm probably going to spend most of my time sitting here just because it's going to be easier for me to operate this. So anyway, the title of this is The Beginner's Guide to the High Frequency HF Radio Experience. This part 1 is going to be about looking at, trying to arrive at an understanding about how your station performs, and in terms of efficiency, what you can do to make changes to improve the performance of your station. The second part will be on standing wave ratio and a practical, from a practical viewpoint. So it occurred to me the other day that somebody might not even know what we mean by HF radio. So I printed off a list of part of the spectrum here. Some of the lower frequencies are called medium frequencies. That's where our AM radio broadcast band is. And if you could tune your AM radio in your car just a little bit higher in frequency off the top end of the AM band, that's where you would find the 160 meter ham band. Now the frequencies from 3 to 30 megahertz is what's called high frequency. So that's basically what we're going to be talking about in this two-part talk. And I've just listed off the different bands by their frequency and in referring to the different bands in terms of their wavelength, those are very rounded numbers. If you take the time to calculate wavelength versus frequency, you'll see that. But I don't want to get into all of that. I want to stay at a pretty high level throughout all of this. 6 meters and 2 meters falls in the category of very high frequency, the VHF band, and our FM radio broadcast band is in between 6 meters and 2 meters. And then we've got some bands up on UHF, and of course there's frequencies much lower than what I've listed here and frequencies much higher. Some of them are called very, very high frequency, extreme high frequency. I forget all the different categories, but we're going to be focused on this area right here in the middle, the HF bands 3 to 30 megahertz. You probably have all seen this. The ARL has a nice band chart that you can print off on your computer, and I keep this by my logbook, well, actually by my keyboard. I've got this memorized from experience, but it's still kind of nice to have to refer to. Now, what we're going to talk about is, I want to start out this morning trying to establish begin to establish an understanding of what a decibel is and how it relates to everything we're going to experience on the radio, and how we're going to deal with decibels when we do a sort of a high-level technical analysis of what's going on within our station. And we'll have to work, we'll start out in the beginning defining what a decibel is, and then as we go through the talk, I'll try to expand on that in practical terms so that you have a feel for what you're hearing on the radio and what you're observing on your signal strength meter, for example. And we'll just build on that whole concept of what a decibel is. So we're going to eventually take a look at how we can add gain into our system, for example, to make our transmit signal louder, or how we can both improve our transmit signal as well as our receiving capability by adding gain in the antenna. I'm going to start out defining a basic station in modern day terms. We're going to use that as the reference that we're going to compare everything to when we start talking about decibels and adding things up and subtracting things. We'll take a little bit of a journey down history, look at a 1960s version of things, and then we're going to go through what's involved in analyzing performance and efficiency. We'll summarize transmitter power out, antenna gain, and loss in your system. And then the second part will be SWR. So there's 3 significant things in the title of this talk. The first one is performance, understanding performance. For the purpose of this talk, I'm defining performance as the on-the-air results that you get with your station, whatever you might have at the moment. We'll talk more about that as we go through this. Efficiency, we're going to take a look at, we're going to do a high-level technical analysis of where we can add gain in decibels, both for transmit and receive, and where we can identify losses in decibels or a fraction of a decibel, and look at the significance of that and look at ways that we can minimize that loss. And of course, SWR doesn't add anything really good to what we do. It certainly doesn't add a gain. It adds a certain amount of extra loss. And what I want to do in that second part of the talk, perhaps next month, is to explain the basics of how SWR works, but then go through very clear practical examples of what different values of SWR, different ratios, what does that really mean in terms of impact on the loss in the system and how that may or may not affect the performance that you get on the air. So that's where we're going to be headed with that. Oh, and everywhere throughout this, is the decibel is going to show up one way or the other. Okay, so what is a decibel? We in the RF world, we compare a lot of things as far as one power level to another. So decibels are. I'm not a mathematician. I'm not going to try to get into logarithms. We don't need to do that. All we need is some simple understanding of power ratios and how that, what a particular ratio represents in terms of decibels. And we're just going to be able to, all we need is simple arithmetic, adding and subtracting. And I put the formulas here for the logarithms. We're not going to touch that. Now, I worked for Bell Telephone Laboratories, later known as Bell Labs, for a long time. And it turns out that in the early part of the last century, it was Bell Labs, as part of the Bell system, that did extensive research on, for the sake of how to develop the telephone industry, did a lot of research to figure out how to measure and refer to power gains and power losses. And so they named, in honor of Alexander Graham Bell, who gets credit for having invented the telephone, they came up with the term Bell, B-E-L, capital B. And I have to tell you, 33 years at Bell Labs, taking all kinds of specialized courses in-house to learn about telephony. Nobody ever told me about a B-E-L, a capital B. I never heard of the term Bell until I was doing some research here. So a bell represents, one bell represents a power ratio of 10 to 1. 2 bells is 100 to 1. 3 bells is 1,000 to 1. I've never heard anybody talk about it. I've never heard anybody use it. We've all been taught, in my life's experience, we've been taught decibels. 1 decibel is 1/10 of a bell, therefore 10 dBs is 1 bell. We're going to talk strictly decibels. We're never going to hear the term bell. Now, all kinds of different sciences deal with the bell. We got the audio world. We measure the loudness of sound in decibels. There's, of course, the electronics and radio world that we're going to talk about. There's control theory, acoustics. Anyways, the bottom line is science has determined that the smallest change in the loudness of sound that the human ear can detect is 1 decibel. Now, if you're new to this, the decibel by itself doesn't really mean anything. So as we go through this, we're going to try to establish a practical understanding. For example, if you double your transmit power, how many dB does that result in increasing your transmit signal? And what does the ear actually hear? It turns out Bell Labs did a lot of research in understanding how the human ear works as part of trying to develop the telephone industry. And I'm not an expert on the human ear, but the human ear doesn't work linearly. So if you increase power by, like you double your power, for example, from 100 watts to 200 watts on the radio link, when you hear that change, doubling the power doesn't turn into being, that signal being twice as loud because you double the power. In fact, you got to increase the power by a factor of 10 before your ear thinks it's twice as loud. At least that's theoretically what they say. My ear may not work that way. Okay, I'm actually hearing impaired in one ear. Okay, so we'll try to develop this as we go through. Now, as far as You've probably seen a list of different things we encounter in our daily life and how loud it is in terms of decibels. For example, a gunshot close up is 140 dB, and that can really, I fired an automatic military rifle years ago, and the guy didn't have me put earpieces in. I thought somebody stabbed me in the ears when I pulled the trigger. Okay, so what's the reference for listing different sounds in terms of decibel? I always just said to myself, well, if a lawnmower is at 90 decibels, that means it's 90 dB louder than total silence. This says 0 dB, which is our reference, is something barely perceptible or near total silence. And I thought about that. Probably throughout our daily life, we're seldom in a situation where there's absolute total silence, for whatever that's worth. So all these decibels are in reference to essentially silence. Now we're going to develop our own references as we go through this radio talk. Now, we're gonna be starting out with a basic station consisting of a transceiver. I'm going to use a half-wave dipole as my reference antenna for a lot of reasons that we'll talk about. And of course, we have a transmission line that connects the two together. So we got three pieces here that we're going to talk about as we go through this talk. We're going to talk about the transceiver, the antenna, and what goes on with the coax, whatever your transmission line is. Now, just as an afterthought, I put on here that there's the audio world and the RF world. I'm here to talk about the RF world, but I'm going to acknowledge that although I didn't draw a speaker or a pair of headphones here, on the audio side of things, we've got an AF audio frequency gain control on our radios, which we think of as a volume control. And so when we're adjusting the volume on our radio to get the loudness of things to be comfortable to our ear, we're basically adjusting the decibel level of the audio coming out of the radio. But we don't think about that. It's just the audio. It's just the volume control. But the point I want to make is whatever we're receiving on the RF link, whatever, for example, we got a signal up here and noise down here, or multiple signals at different levels. What comes out of the audio side of the radio, whatever those relationships are on the radio link, as we adjust the volume up and down, those relationships remain constant. We're just adjusting the volume of the sound coming out of the radio, okay? Enough said on that. I probably didn't even need to say that, but we're going to concentrate on the RF world. Now, I'm somebody that's always been fascinated with working DX on all the different bands on both phone and CW. I just love trying to work weak signals that takes some doing to make those contacts happen. So in between our two antennas with whoever you're talking to is this mysterious space, whatever. There's a whole science behind radio wave propagation. We're not going to discuss that in this two-part talk. We're going to talk about what happens and what we can do at each end of the path in terms of transmit and receive, but we're not going to deal with what happens mysteriously in between. We did have a talk last year on propagation. Perhaps we could revisit that in the future. But the point I want to make here is that the reason I'm still in ham radio after all these years is that the mysterious things happening out there as part of radio propagation is constantly changing and is never the same. If this radio stuff was like turning on an intercom and having perfect quality communications all the time, I would have lost interest the second day I got into this. To me, it's the fascination of the mystery of this all. And the point I want to make before we continue on is You may have a friend that you talk to. Maybe you have some people have schedules like almost every day to talk to a friend or a family member. And you're on a particular ham band on a particular frequency, and perhaps you meet at a particular time every day. There's going to be no 2 days that will be exactly alike. There may be days, depending on where that other person is, there may be days you can't even make the contact because of what's happening in the middle there. There'll be other days where you're loud and clear. It's constantly changing. And some of the things that affect that, of course, it changes moment by moment, hour by hour, whether the path is over darkness or daylight. We have the 29-day rotation of the sun, where the sunspots are rotating towards us and away from us, that affects propagation. The seasons play a role, the equinox, and we have the 11-year sunspot cycle that we're approaching now. The conditions are pretty good, I mean really good. We have solar storms and flares. We had a good example of that last weekend. And there's all kinds of other strange things like sporadic E-skip and ducting. We're not going to be dealing with any of that in this talk. That's the mystery that makes this fascinating to me. I know I'm pointing at the screen. You can't see what I'm pointing at. But okay, let's talk about 2024, and let's establish a reference, a baseline on which we're going to build as we go through the talk. So here is a Yaesu FT710 modern day radio. AESS stands for acoustically enhanced speaker system. Bill has one of these. He's going. My friend Bart, who couldn't be here, has one of these. He had me play with it for 2 weeks at my house. The point I want to make here is, those of you that are relatively new to this hobby and are starting out in this modern day we live in, you can go out and buy, I'm not here to sell Yaesu radios. I mean, if you go out and buy a modern day radio like this, or a Kenwood, or a Nikon, you are getting an amazing piece of technology in a relatively small box. And although it may cost you upwards of $1,000, you're getting a lot of money. You're getting a lot of capability for the money. And so most people today start out with a transceiver that runs 100 watts output. So we're declaring right here and now that our baseline, our reference from the standpoint of power, is 100 watts, and we're going to build on that as we go through. Next comes the antenna. We're going to use the half-wave dipole as our reference antenna. We'll talk a lot about that when we get deeper into this. I decided to show a photograph of a rotatable or rotary half-wave dipole because it shows up better than a pair of wires hanging up there in between trees or whatever. There's another reason why I'm showing this, because a half-wave dipole is a building block for many antennas. Our Yagis, our beam antennas, those elements are essentially half-wavelength elements adjusted a little bit to make them either reflectors or directors. We'll talk about that at some point. So we're going to declare a half-wave dipole as our baseline reference antenna. And we're going to say that compared to other antennas, the dipole is 0 decibels. So we got 100 watts for our baseline for power. Our dipole is our reference antenna for 0 dB. And here is a little bit of trivia that may come as a surprise to a few people. I started out with a wire dipole when I was a kid. We're going to talk about that because I did some really dumb things. By using a half-wave dipole as the reference antenna and comparing the gain of other antennas to the dipole, ideally the way you have to make that reference is you have to have your dipole up here at a given height and your other antenna at the same height. And then you can actually do real comparisons to see how much extra gain your beam has versus the dipole, okay? The rotary dipole has the entire length of the antenna essentially at the same height. very few of us can put up wire dipoles where the antenna's at the same height. You got it strung between trees, you got sag, you may have it uneven, you may have an inverted V where the center is at the same height that you would have a rotary dipole, but you got the wires coming down, okay? Now the bottom line there in red may come as a surprise to people, but an inverted V can be anywhere from 6 to 10 decibels lower than a rotary dipole, all at the same height as the center of the inverted V. But I found this interesting, that by having an inverted V with the wire sloped down, your average height of the antenna is much lower. You distort the radiation pattern from a dipole, which has radiation, and we'll see this later, broadside to the wire. When you slope the wires down, the pattern gets altered to more of an omnidirectional antenna. There's some other mysteries here that I'm going to leave a mystery till we get farther into the talk. I was not aware that there could be such a dramatic difference between an inverted V with the center at the same height as a dipole that's all at the same height. I get the authority for that from Mr. Tom Schiller and 6BT, who founded Force 12 Antennas years ago. And he's got this book he wrote, which I'll be referring to. And one of the many things that he has in there is proof of some of these things, like how the performance changes with an inverted V. I got to get my voice back here. Okay, so why show a picture of a piece of coax? Okay. It turns out the coax, or whatever feed line you use between the transmitter and the antenna, is very important. And there's a lot of things we should know about the transmission line that we can use to our benefit. There's a complicated science associated with feed lines called transmission line theory. The point I wanted to make here is that we're going to talk about how we can add gain to the system by increasing our transmit power. We're going to look at how we can add gain to our station with antennas that will improve both transmit and receive. The feed line, the issue is loss. You're not going to introduce any gain with the feed line. The question is, how can we minimize the loss of power between the transmitter and the antenna and vice versa? And it's worth spending some money for a decent feed line. We'll get into that. Okay, so coax always introduces loss to some extent and never adds gain to the big picture. All right, a little bit of history. I'll go through this rather quickly. Part of this is my history. Okay, but this was a typical 1960 novice station. Okay, we didn't have as many transceivers back then as we had separate transmitters and receivers. There were some transceivers, but back then we didn't have solid state radios. Everything was vacuum tubes. In order to put a transmitter and a receiver in the same box, you had to make some compromises to keep that box a reasonable size. And if you had a receiver with all kinds of fancy features and bells and whistles that were neat in that particular time in history, we got much better stuff today. But in order to fit a transmitter and receiver in one box, there were compromises that were made, and you had normally you had a pretty basic receiver, okay? Enough said about that. But when you have a separate transmitter and receiver and one antenna, you got to switch between the two. Well, guess what I was told when I got started as a 12-year-old kid? Go get yourself a double pole, double throw a knife switch. And when you want to transmit, you throw the switch to the other position. And when you want to go back to receive, you switch back the other way. Okay? Now, this is my 1960s story. I'll do this real quick. 1958, cycle 19 of the solar cycle 19 was the highest, most intense cycle in recorded history. In 1959, it was still near its peak. I went to a friend's house. He had a little thing called a shortwave radio I had never seen before. He threw a piece of doorbell wire out his window, connected to the back of the radio. And that afternoon, we listened to 10-meter AM phone. Now, we've not experienced this for the most part in ham radio since, but that afternoon with that intense cycle, the entire world, every continent, every corner of the world was coming through incredibly loud all at the same time. That normally doesn't happen because the propagation is affected greatly by whether you're going over daylight or darkness. But things were so good. We were hearing Europe and Africa, South America, the Far East, everything all at once. And I immediately fell in love with this radio thing and determined right on the spot that this was what I had to do. Ended up being for the rest of my life, okay? So I got my license in 1960. Now, I joked with people, if you've heard me talk about some things before, I say if it were possible for somebody to know less than nothing, that was me at 12 years old. We had a hometown radio club. All I knew is I wanted to do this, but I had no clue about anything. So I joined the club. They were mostly all adults, me and my buddy. He got his license too. So we were at the mercy of whatever we could pry out of the adults, okay? There were no books. I couldn't afford anything. My parents weren't well off, so I had to scrimp money together. I certainly wasn't going to pay money for books. I needed every penny I could get for equipment, and there was no internet, so I was helpless, okay? Now this is a list of what my early stuff was, and we're going to look at that real quick. So here was my first attempt on the radio. I put my little novice station together. I couldn't make any contacts. And so I was extremely upset and unhappy. This was all just a pile of stuff and nothing was working. And I'm sure my dad got tired of listening to me whine, so he called the president of our radio club and basically said, hey, could you come over here and maybe help my son and find out what's not working? Now, I was 12, the president of the club was 30, and he was a very surly, sarcastic kind of a guy. So he showed up at our house with his attitude. And we first went in the backyard, me, my dad, and the president, to look at my dipole antenna. He wasn't there but seconds, and he starts laughing, and I know I heard the word stupid between him and my dad, okay? Here's why. I didn't have coax cable. Nobody told me anything about coax. I looked up in the Allied radio catalog, and I ended up buying microphone cable of who knows what impedance that was. I wired my whole station inside up to that knife switch with microphone cable and then on out to the antenna. So my club president had a good time laughing at how dumb I was. Okay. So cable, the right cable makes a difference. I then found out I needed 50 ohm coax. I still didn't know what that meant, but I was able to get enough information to order some real coax, and bingo, now I was ready to go. Now, this was my first novice station, and there's several reasons why I want to show you this, because this was back late 50s when this first came out. I bought it in 1960. It was a night kit from Allied Radio. My dad helped me put it together. This cost a whopping $38.95. It has 3 tubes in it. It's got an 807 final. I think there was a rectifier tube in the power supply. Yeah, and then there was a little vacuum tube in the oscillator driver stage. Now, novices were only allowed to run 75 watts of power. This T50 says this was a 50-watt transmitter. The tube was an 807, and I haven't heard this in many, many years, but when I was a kid, when the adults got together and say, hey, let's go get a beer, they didn't say, let's go get a beer. They said, let's go have an 807. Probably because an 807 was about the size of a can of beer. That's what I think. But for many years, hams didn't talk about having beer. They said, we're going to have an 807. Now, novices were crystal controlled. We could only transmit, we had to have a separate little crystal that vibrated or oscillated as tuned for a specific, cut for a specific frequency. What that meant was I would plug a crystal into the front of the radio here, and like if I wanted to call CQ to try to get somebody to talk to, I would be calling CQ on my crystal frequency, but probably the people out there, their crystals don't match up with mine. So when I get done calling CQ, I got to tune my receiver back across the novice band, hoping to find somebody on another frequency answering my CQ. There was no main tuning dial like on a transceiver where you're changing both the transmit and receive frequency at the same time. We were limited as novices to crystal control. There was a slot in the front here next to the crystal slot to plug in a VFO that would let you tune around the band with your transmitter, but I wasn't licensed to do that yet because I was a novice, not a general. Now the thing I want to point out here is this was a vacuum tube radio, and the two knobs on the right-hand side of the radio here were used to, vacuum tube radios had to be tuned up, not like solid state radios. If you started with the modern world, you've never had the experience of tuning up a vacuum tube radio. So those two knobs on the right there, you would advance the top knob to try to bring the plate current on the tube up a little bit. You'd adjust the bottom knob for what's called a dip, which is indicating resonance. And you'd advance the top knob and find a dip, advance the top knob and find a dip, till you reached 110 milliamps of plate current, which was the rating on the radio. You had to go through that process. Now, those two knobs basically represent, you can think of it as a built-in antenna tuner. Because the output impedance of a tube is very high, I don't know what that impedance actually would be in those days with that tube, but you're trying to work into an antenna with a much different impedance. So the output stage of your transmitter, in effect, is a tuner, and you're trying to adjust things to match one high impedance, the tube, to the antenna. I wanted you to hear that and see that because it's going to play a role in things we're going to talk about. Here's a picture of some crystals. I could only afford 2 crystals. I don't remember what I paid for them, but I had 2 40-meter crystals. That was it for my first year or so of operating ham radio. My first receiver was a Night Kit Space Spanner. I actually bought that as a shortwave listener prior to becoming a ham, not realizing that that was a piece of junk when it comes to trying to use it as a ham radio receiver, okay? I won't go into the reasons why. Here's a typical knife switch. Just picture taking your coax, no connectors, that's a bad thing to start with, split the wires out, put the center conductor on one side and the shield on the other, all open, exposed. That's how I started out, throwing the switch back and forth between transmit and receive. Later, when I got a little more educated and had a little extra money, there was something called a Dow key antenna relay. You can see on one end you connect the antenna, the receiver on the top here, the transmitter on the bottom. I got a piece of lamp cord with a plug on the end and a switch. This would run off 110 volts. Plug this thing into the wall outlet. When I wanted to transmit, flip the switch, the relay would switch from the receiver to the transmitter, and then when I want to go back to receive, throw the switch the other way. Obviously, the modern world we live in, all this stuff's built in automatically in our radios today, okay? This is when I actually became a real ham. I have a buddy in Illinois. We've been buddies for 55 years. Bill knows about this. I think I told Bill. He jokes with me because I'm an old timer. I'm a dinosaur. I don't like change. I stick with old things. And so he says I'm not a real ham. And that's another story. In 1960, I became a real ham for the first time when I got this Hallicrafter's SX28 receiver, which was introduced to the world in 1941. And I got it used for around $100 in 1960. Fortunately, my parents were able to help a little bit that I could buy that. I loved collecting QSL cards, especially when I was a kid. Every day I would run to the mailbox and look for a card. One day I ran to the mailbox and I get this official looking letter with my name on it. It says Federal Communications Commission in the upper left-hand corner. And I open this letter up and this official citation, I'm paraphrasing, but I'm not exaggerating. It says, "Thou shalt immediately cease and desist all radio transmission." Talk about ruining a 12-year-old kid's day. My little night kit T50 developed a spurious emission, a parasitic oscillation, which meant when I was transmitting on Morse code on the 40-meter CW novice band, I was also transmitting a signal on 5-point-something megahertz right on top of a Canadian broadcast station. So I've just been told, thou shalt not ever transmit again until you fix this problem. So how does a 12-year-old kid fix a parasitic oscillation? I don't even know what it is. Well, the bottom line is I couldn't find an adult in the club who either knew anything about it or was willing to help this dumb kid. I had no choice but to scrap that transmitter and start over. So that led to the next night kit called the T60. This is a night kit T50 on a little bit of steroids. It's now 60 watts, but it came with an AM modulator in it. So now I could work phone when I got my general license. You can see that you can still plug crystals or a VFO into the front of that. But that was the cheapest radio I could get to replace my piece of junk T50, okay? In the latter part of 1960, I passed the general test, and I bought a night kit variable frequency oscillator, which plugged into the other socket in the front of my radio. And now I've really hit the big time because I can find somebody on my receiver and I can then tune my transmitter to the same frequency, and we can talk to each other and not be on separate frequencies. So that was the end of crystal control for me. And my first amplifier was a little 400 watt amp, enough of that. So here's the bottom line. I was a kid. I was thrilled to death about this radio stuff. I knew absolutely nothing. Nobody ever mentioned the term standing wave ratio to me. If they did, I wouldn't have a clue what they meant. I would say I went through the first 4 years of the hobby not knowing anything about standing wave ratio or power. So I had no SWR meter, no SWR bridge, no watt meter to measure power out or reflected power. I wouldn't even know what reflected power meant anyway. And we certainly didn't have modern day antenna analyzers like we have today. I just put up wire antennas, starting with microphone cable, and my antennas were always probably more like 25 feet or less off the ground. I said 30 here. I lived in a very poor location between a 4-story factory and a gigantic church. Horrible location. Nevertheless, running all this little bit of power, well, I did have an amp at one point. From southeast Pennsylvania, I was able to work all 50 states and not quite 100 countries. That was my early years' experience. Okay. Now, let's talk about performance as I'm going to define it. Quoting Tom Schiller, N6BT, who had the company Force 12 antennas, he wrote this really great book. I recommend it if you want something other than just a great reference book. This is a very practical book about how things really work in practical terms. He says that everything does work to some degree or another. And this circle stuff in the middle is illustrating that whether you're a new person starting today or you've been around a while, if you got an existing station, you've been around a while, you can declare your starting point wherever you happen to be right now. That would be the center of the circle here, the red. And there is always room to improve the performance of your station. Now, my point of view would be that when you start out, you've got to get on the radio and use it in order to develop some practical understanding of what you can and can't do with your radio. You may find that you can work people in neighboring states, but when it comes to real long distance contacts, it's not working so well. You just have to get it's a whole new experience when you start out from scratch. You don't know what to expect. You're going to be, anything you hear and anybody you can talk to is going to be fun and exciting. But no matter where you are in the ladder, the food chain here, there's always a limit to what your present situation, your station is capable of doing. So this is illustrating there's always ways to add to the performance, make a change to your station to increase the performance. And that comes down primarily to identifying where we can add gain into the system and where we can identify and either eliminate, or if not eliminate, minimize loss in the system. Okay, and so that's some of the things we want to talk about. A little radio history. It was in the early 1880s, there was a man by the name of Maxwell who was the first person to theoretically state that there was the existence of something that became known as an electromagnetic wave or electromagnetic waves. He was working in the theoretical world. I'm not going to go there, but in 1887, a guy by the name of Heinrich Hertz ran the first actual experiments. He actually created some electromagnetic waves, and he gets credit for having really proved the existence of electromagnetic waves. Now, when I became a ham, we referred to frequencies in terms of cycles per second. So 40 meters would be 7,000 something kilohertz, kilocycles, or 7 point something megacycles. Sometime in our past, I don't remember what year, the world decided to honor Mr. Hertz, and therefore we no longer refer to frequency in terms of cycles per second. It's hertz per second. 1 cycle equals 1 hertz. That's just common knowledge to people today. I remember when that was a painful change. It's like, I understand all this cycle stuff. I've been taught what all that means. Now you're telling me that this is going to be hertz, but that's the way we do things. So we now have frequency in terms of hertz per second. Now, we all probably know that Marconi in the late 1800s and in like the first 1901 or 1902 made the first successful radio transmission from England to Newfoundland across the Atlantic. I don't want to spend a lot of time here, but if you haven't read about that, you might Google his name and read a few things on the internet, because radio was new. They didn't know what they were doing. Okay, everybody has to learn. So they were using, I'm pretty sure it was a spark gap transmitter, which is spewing energy out on all kinds of frequencies. They thought that they were operating on 850 kilohertz or somewhere down there, which is below, that's like in our AM radio band. They transmitted in Morse code the letter S, and supposedly the guy in Newfoundland heard the dit, 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 okay? They get credit for the first transatlantic radio communication. But we didn't have nobody knew about things called tuned circuits in that day. The path when they ran that experiment between England and Newfoundland, it was in daylight on a very low frequency. We now we understand that that path likely didn't exist at that frequency between England and Newfoundland. And we didn't have tuned circuits, so we're transmitting on a wide band of frequencies and receiving on who knows what. Wherever that guy that heard the dit on the other end, he probably wasn't hearing that on 850 kilohertz. He was hearing it on some other frequency. I just find that fascinating. I don't know if I explained that well. Okay. But so the point is, in the early 1900s, radio was brand new. The sciences associated with all this had yet to be developed. Now, in 1914, a guy by the name of Hiram Percy Maxim, along with a friend of his who never gets any credit, I should have looked up his name and put his name in here, but Maxim got credit for co-founding the American Radio Relay League. Now, I often wondered, why did they call it the American Radio Relay League? So I checked it out, and in 1914, they kind of understood now that it was possible to communicate by wireless, by radio over distance, but they didn't really know how to do it effectively or reliably. And so what they envisioned was creating a network of stations. They wanted to be able to communicate from the East Coast to the West Coast of the United States by radio, but they didn't really know how to do that in one 3,000-mile path. So they envisioned creating stations, short distances apart, maybe a couple hundred miles, and we would pass a message from one station to the next and relay it to the next station until we get to the other. Therefore, they called it the American Radio Relay League, and that exists today. Now, in the early days, when you make a contact with somebody, everybody wants to know, well, how do I sound? What's going on with my signal? There was no uniform set of rules established on how to exchange signal reports. So in 1934, this guy named Arthur Breton, his call was W2BSR, he developed the RST system, which 90 years later today, we still use pretty much universally in the hobby. RST stands for readability, strength, and tone. So here we are 90 years later, and we still use that. So it's a three-number scheme to everybody gets familiar with the numbers, and so all you have to do, like on CW, is send three numbers, and that immediately is supposed to convey some meaning to the other guy, the other person, as to how understandable your signal is, how loud it is, and if you're transmitting in Morse code, is the sound of your note, is it a pure, nice sounding tone, or is it all basically screwed up? Okay, so the first number, R, is a number from 1 to 5. You can see there. I don't want to spend a lot of time on this. The second number, I'm going to tie directly into what comes next, and that's signal strength. We have what we call 9 S units, going from 1 to 9, and just look at that. Faint, barely perceptible, very weak, fair, fairly good, moderately strong. You sit down 6 people, listen to one signal, you're going to get 6 different interpretations of what that number should be, right? If you're on code, the number goes from 1 to 9, and it has to do with whether your tone sounds nice or whether it sounds horrible. I'm not going to go into the history of what caused all these weird sounding things. But early radios that had variable frequency oscillators were oftentimes unstable. And I saw this as a kid. You'd turn somebody in on your receiver, take your knob off the dial, and all of a sudden they drifted up or they drifted down. If it was really bad, you got to sit there and keep tweaking your receiver because the signal was unstable. That was a big problem years ago. So if you were transmitting and your signal was very stable, they would sometimes put the letter X after the last number to say that you have the characteristic steadiness of crystal control. Okay, if you had a chirpy sounding note, they put the letter C after it. And today we still have transmitters in the modern world that have key clicks that you hear all over the place, and you can put a letter K after that. Okay, I think I summarized, I already discussed much of what you see on this chart. From a practical point of view, very few people on the air try to use the RST system and give you like a 139 report or a 239 report. If you get a report like that, you're kind of unhappy, like, wow, the guy barely hears me. So what happens most of the time, if somebody tells me I'm 5'9", okay, so he has no problem hearing me and I'm good. Now this is just my opinion. If I get a report that says 5'5", that's not so great. I mean, okay, he's hearing me, but I find on the air, you're either 5'9" or you're 5'5". You will hear people who try to conscientiously give you legitimate reports, and sometimes I'll sit there and laugh. Like I recently heard somebody get a 1-something-9 report, and I thought, so this is working, huh? Readability 1. Anyway, if you're into DXing, like DXpeditions, or if you're into contesting, everybody transmits 599 as part of the required exchange. In the DX world, you don't care what your signal strength is. All you want is to complete that contact. So logging software today automatically sticks 599 in there everywhere, okay? Contesting software, if the exchange includes signal report, it's automatically plugged in 599. Now, because everybody's trying to go in a big hurry, make as many contacts as fast as possible, they even have a shorthand, like on CW, a 599 report, 9 is da, 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 dit. You gotta do that twice for 2 9s. That takes too much time. So now you said 5NN, an N is da dit, a 9 is da, 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 dit. 5NN means 599, that's the shorthand. Okay. So the last point is, if you like to get on the air and rag chew with people, you may get a more honest report from somebody that you're just casually chatting with and you're trying to understand what's going on. They may try to give you a more accurate, honest report. But DXing in contest, forget it. Now, a direct outgrowth of this RST system, the middle number signal strength led to something called the signal strength meter. Now, there's a lot we can say about this, but I looked for, this is a pretty basic meter, but I wanted something that I could have here that you could easily see on the screen. The signal strength meter is calibrated so that the center scale of the meter is S9. So everything to the left of 9 going down is supposed to be calibrated as individual S units from S1 to S9. The International Amateur Radio Union got together years ago and declared that 1 S unit is equivalent to 6 decibels. Okay? I told you earlier that the science says that the human ear, the smallest change in the loudness of a sound that you can detect is 1 decibel. Okay? So crammed into this little space on the meter, those little calibration points, going from S5 to S6, for example, is supposed to represent a 6 dB change. And I'll just tell you out of sequence here that if you double your transmit power, that's only 3 dB. We're going to look at that more closely a little later. So if you double your transmit power, you might see the S meter go up by half an S unit. Okay? It's not going to be a huge difference in what you hear, okay? But anyway, so on the left side of the meter is S units. The right side is signal strength exceeding S9. Now, I knew a guy, an adult years ago when I was a kid, who didn't understand some of this, And he thought that when you went from 9 to 20, that we went from S9 to S20. Okay? To the right, above S9, we're then talking about decibels in excess or decibels above signal strength 9. So you would typically say 5.9 plus 20 decibels, 5.9 plus 10, 10 over, it's different. Now the point is that this meter is in no way a precise measuring instrument. It's anything but a precise instrument. It's just giving you some relative sense of what's going on the radio link. The calibration could be way off from one radio to the other. There's a standard established by the International Amateur Radio Union that says S9 is supposed to represent a 50 microvolt signal at the input to your receiver, assuming the receiver has a 50 ohm input. So the calibration, the manufacturers are supposed to calibrate the S meter, and they come in modern versions now like LED bar graphs, liquid crystal displays, blah, blah, blah. But originally we have an actual meter movement here. S9 would represent 50 microvolts into a 50 ohm input. Now, 50 microvolts, that's only 50 millionths of 1 volt. Okay, what happens if your signal's down near the bottom here? You're down to like a fraction of 1 microvolt. It's just fascinating that we can transmit this invisible energy through the air. The receive antenna grabs a hold of it and induces a voltage into the receiver that's just, in some cases, a couple of microvolts. But that's part of the big fun and mystery. Now, these meters if they're calibrated according to the standard at S9, your accuracy immediately is going to it's going to become more inaccurate as the meter goes lower or higher. So there's nothing precise about this in any way, shape, or form. And where these meters get their signal to deflect the meter can be at various places in the IF of the radio or after the automatic gain control circuitry. The automatic gain control tries to maintain a constant volume or constant signal strength, which means on the radio link things are bouncing around, but the automatic gain is trying to keep the level at a constant level. Okay. Now, I don't know much about software-defined radios, but I'm told from what little I've read that if you have a 14-bit software-defined receiver, these new radios, you'll be able to go in at the bit level and actually determine the exact signal strength, precise signal strength at the input to the radio. Okay, I don't know enough about that to proceed, but supposedly we're going to be able to measure more accurately, with more precision, with a software-defined radio, measure signal strength compared to the way we did things here. Okay. I think I covered most of this. A couple points I want to make. When you make a contact on the air and somebody says you're S7, maybe they're telling you you're S7 because their S meter says S7. All that is telling you is that at that instant, in that moment in time, over that particular path between you and that station, with whatever the propagation conditions are at that moment, you happen to be S7. You know, if you talk to them for an hour, you may experience fading, or your signal may go away, it may get louder. So this relative meter, this S meter is a relative indicator that tells us something just at that particular moment. Now, where this comes in to be of more value is if you're talking to somebody and your conditions are fairly stable and you're S7 and you're running 100 watts and you switch on an amplifier, you will be able to hopefully hear the increase in the loudness of the signal with your ear, but you'll be able to observe that on the S meter. However, because of the inaccuracy of these meters, it won't necessarily indicate exactly what the change is. You know, like if you went from a 100 watt transceiver and you switched on an amplifier running 1,000 watts output, that's a 10 decibel, 10-fold increase in power, which happens to be 10 decibels, which is not quite 2 S units, okay? You should be able to hear that, and you should be able to see some noticeable change. But again, it's all relative. Now, if you've got a rotatable antenna and you want to learn something about the pattern of your antenna, you can point it at the guy and he can tell you, oh, well, you're S8. Then you can turn it over here and, oh, now you're down to S6 or S7. S7. Turn it all the way around and see what the front to back ratio is. You know, at that moment in time, if there's not a lot of fading, you can get a sense of these relative differences. Okay. Now, the bottom line on this is that the overall quality of our communication, our comfort level of our communication, is going to be determined by how much noise you happen to have to live with where you're at. And we live in an our world is increasingly more polluted with electrical noise. It's running many people off the air, okay? I think we're doing pretty good on time here. That's a lot of words. Let me just try to summarize what I got written up here. The very important thing in everyday communication is your signal strength up here and is the noise down here. The greater the difference, obviously, between you and the noise is referred to the signal to noise ratio. And if you're in a noise polluted environment and your signal is basically at or slightly below or above the noise level, and isn't going to sound all that great, okay? So if you're running 100 watts, maybe you kick in an amplifier and you can increase the transmit signal, the receive signal. But noise is a huge issue in our modern world. My friend in Illinois has got a really great radio station in a suburb of Chicago. He cannot get on the air and operate because he has so much noise from so many sources. He's thrown up his hands and given up. On the higher bands, his S meter sits at S9. On the lower bands, it's 10 to 20 over 9. Wow. Hence, FT8, okay?
But it has limits too.
Right. But there are people today, they have no choice but to do FT8 because they can't hear anything on CW or sideband, okay? So noise is a huge issue. Now, I didn't know some of this in the years past. I used to turn on my radio like on 80 meters in northern Illinois, and my S meter would go sit up at like S8 or S9, just sit there, steady state, with what I would call a constant, like a white noise, okay? Okay, that was propagated noise. It wasn't a local noise. So, I'm getting out of sequence. First of all, our modern day homes are full of all kinds of electronic gadgets that create noise. Wall wart transformers are one of the sources of noise. Now, I'm blessed to have a little bit of land, so my antennas are far away from my house, and I haven't detected any real noise issues coming out of my own home, because I've run tests to determine that. But if you got a lot of noise, you may need to go around and try to identify devices in your home that may need a remedy applied to it. Today we can fix a lot of things with something called common mode chokes. I don't have time to get into that. But if you have a noise problem, it may be a local noise or it may be a propagated noise. If it's local, if it's in your house, then that's good news because you may be able to find it and fix it. If it's in your neighbor's house, I hope you're good friends with your neighbor, okay? Now, if you don't have a lot of local noise that will mask out what I'm about to say, you should be able to observe that on the ham bands, on the HF bands, some bands are open for long distance when it's dark out, and other bands are open for long distance when it's daylight. So take one of those bands, like in the morning, if you're sitting on your radio on 20 meters, prior to the sun coming up. At my house, my S meter's sitting down at 0. There's pretty much no noise. But if I sit there and through sunrise until the band has opened up, and it opens to Europe in the morning typically, now I can actually watch my S meter go from 0 just gradually as the sun's getting higher in the sky. My S meter will go up, and it's not uncommon at my house for my S meter to sit at S6 or S7 on single sideband on my wider filters. Narrow filters on CW, the noise is not really a problem. Years ago, I didn't understand that steady noise that I'm hearing when the band opens is noise propagated over long distance. It's the summing effect of literally countless noise sources propagated over the air, combined at your receiver to produce that white noise. To some extent, you're out of luck. Let's just put it that way. To some extent, you're out. You can't fix those problems, but there are special low noise receive antennas and directional antennas that we can use to try to deal with propagated noise as well as local noise. Okay, so you can have. The point I want to make is if you're trying to work signals that are right at the noise level, I'm getting ahead of myself. Let me back off that. You can deal with noise by having special low noise receive antennas. You can take two separate antennas, phase them, and cancel noises coming from certain directions. We can get rid of certain noises with noise blankers in our receivers, like impulse noise, ignition noise from a car. We have some dynamic noise reduction algorithms, which may or may not be of any great help to you. And common mode chokes or something. We could come back and do a whole talk on noise, finding and fixing noise. Okay. Well, maybe I wasn't ahead of myself. Let me back up. If I'm listening to a real loud signal, let's say the guy's 20 over 9 on my meter, way, way above this noise level, and then we would have him do something. Well, maybe the conditions are so fantastic that he's running 100 watts and he's 20 over 9 at my house. The rules say we were supposed to run minimum power to maintain communication. Nobody pays attention to that. But let's say you switch on a 1,000-watt amplifier, which is going to provide 10 dB a gain. First of all, you don't need it. He's already 20 over 9. You're probably not going to really notice it all that much because he's so loud. You're probably not going to pay that much attention to the meter. But if you're trying to work this guy and your noise level is S7 and his signal is at S7, and he goes from 100 watts to 1,000 watts, he's suddenly going to jump up above the noise, and that's going to make all the difference in the world. Now, I like to chase DX on the low bands, like on 160 meters on CW, where signals are typically extremely weak. There are many, many times when I'm sitting there in the wintertime, when there's little static, and I'm trying to tweak every bell and whistle on my radio, try to be able to copy this CW signal from some faraway place. There's many times where I wish I had a magic button on my radio that said 1 dB, and if I pressed the 1 dB button, his signal would jump up 1 dB louder than the noise, and I guarantee you under those conditions I could make the contact with 1 extra dB that I couldn't make without it. But I got no such magic button. Okay. The point is, and probably a little out of sequence. You don't want to judge the performance of how your station is working on loud signals. You want to find out what's really going on with weak signals. All right, here's some power ratios. Everybody ought to get familiar with some of these numbers because it'll affect how you interpret and understand what's going on when you're using your radio day in and day out. So if you're running 100 watts and you went up to 112.2 watts, that represents a half dB of gain. 126 watts would be 1 dB of gain. I don't work in those kind of numbers very much. The significant number that everybody ought to be aware of is every time you double your power, you get 3 dB of gain. Every time you lose half your power, you lose 3 dB. And this is logarithmic in nature. So if I go from 100 to 200 watts, I get 3 dB gain on my transmit signal. If I go from 200 to 400, now that's a 4-fold increase, but going from 200 to 400 is another 3 dB and so on, okay? We're allowed to run 1,500 watts output legally. So the reference of 100 watts, which I established a while back, difference between 100 watts and 1,500 watts is 11.8 dB of additional transmit gain or signal. That's basically 2 S units, okay? Just try to get familiar and think of these things in practical terms. So on this side is gains, on the right side is losses. Now, here's a neat little calculator that I recommend you bookmark and you can play with, and I'm actually going to momentarily get out of this, and I'm going to bring that calculator up and show you how easy this is. You can compare milliwatts to milliwatts, you compare watts to watts, or watts to milliwatts. I'm going to be comparing watts. So let's say our output power is 1,500 compared to our 100-watt transceiver. Okay, watts to watts, and bingo, there's our 11.8 dB of gain. I have this bookmarked. You know, you can plug whatever numbers you want in there. Jim, when he did his antenna talk, talked about dB starting out at 1 milliwatt, 1 dBm in referencing. You could do that right here. Let's go to milliwatts, and let's go to 1 milliwatt compared to 1,500 watts. And that's 61.8 dB of additional gain, okay? Okay. So I recommend, there's other tools like this on the internet. You might want to find one that you like. It's kind of fun to play with. Okay, having done that, let's jump back to where we were. Okay. Now, this slide to me is very important. I probably hit on some of this already. Small gains in decibels, in my opinion, are difficult to observe on very loud signals. I just talked about that. And this is kind of misplaced, but I threw in there, you know, the FCC rules say we shouldn't run excessive power if we don't need it. That goes back to the days when the ham bands were so crowded you couldn't hardly find an empty space to fit in between two conversations. So the higher the power, the more interference you're trying to get the most usage out of the band by running the minimum amount of power. I don't think people pay much attention to that. The point is that a very tiny little change in terms of decibels, up or down, on very weak signals makes the difference between being able to make a contact and not make a contact. Now, Mr. Schiller, who wrote this book, A Ray of Light, has a lot of experience and has determined, and I agree with him, not that I'm not on his level, but I got a lot of experience on the radio. If you can improve your station's overall performance by as little as 2 dB, and you're into working, weaker stations, DXing and so forth. If you can have a 2 dB improvement in the performance of your station, you're going to open up a whole new layer of stations you never heard before. Now that's hard for people to understand until you get some practical experience with it. But 2 dB is a major change. Most hams start out with wire antennas strung up in some convenient way, 20, 25, 30 feet off the ground. The first time you go to maybe a tower, even if it's only 30 feet high with a rotatable 3-element beam on it, there's like an entirely new world, a whole new experience that you never knew existed all those years that you used wires. Okay. Now the old timers when I was a kid told me that if you can find something in your station where you could make a 1/2 dB improvement, it was worth doing. Because they said if you could do a 1/2 dB here and a 1/2 dB here somewhere else, it adds up and it will make an actual difference, okay? This may be a little out of place, but as long as I got this book up here. Mr. Schiller mounted a 100-watt light bulb on a 4-foot wooden post. And he ran a coax out there with a Ballon or a common mode choke to make sure that the feed line wouldn't radiate. And the antenna was a 100-watt light bulb. He got into one of the major weekend DX contests on CW on 10 meters. Using the 100-watt light bulb, casually operating on and off here and there throughout the weekend, he worked 41 countries on 10 meters on CW with a light bulb. Downspouts work. So then he got really all enthused. You can't see the picture. A future version of this, I may try to paste this. He created a 3-element array, 3 light bulbs spaced in a triangle. And they tuned the phasing of the antenna by adjusting the brilliance of the bulbs, okay? And he says that this 3 light bulb array has 3 dB of gain SLB, meaning 3 dB greater than a single light bulb. Enough of that, I gotta press on. Okay, now my version of efficiency here is it's not possible to achieve 100% efficiency. In some realms that you deal with, you can identify that some process or some machine or something, you know what 100% efficient is, you know you're not there, you can do what you can do to get and reach the ultimate 100%. Ham radio doesn't work that way. There is no 100%. For one thing, we're pushing the envelope all the time in all the different sciences. We're learning more, doing more. Antenna theory and practice has come light years in the years I've been a ham. There's no point at which you can achieve and say you have arrived, because then the envelope has changed. If you want to know who's up to date, if you have a way of following the guys who are the top tier contesters, I mean the really serious contesters that spend maybe $1 million or more on their stations, and they run 5 stations, 6 stations simultaneously in a big contest. They're at the leading edge of every aspect of every science that comes together so that they can have the competitive edge to try to be #1 in the world. So if you want to know where this hobby is going or where it's at any moment in time, anytime you have an opportunity to learn about what these guys are doing with these huge stations, they're setting the pace for where this all goes. So it doesn't matter where we're at, we can tweak our station, we can make changes, and there's always something new and different to look forward to. If you have the money, if you're not restricted by the covenants and restrictions, there's lots of things that limit what we can do. But the bottom line is identify where you can add gain and where you can minimize loss. And it's simple addition. If you have 3 dB gain here and 4 dB there and a negative loss over here. Just add the numbers together to a final number, and that represents the overall gain of your station compared to whatever your reference is. So if you increase, this is pretty obvious, we'll go through this quickly. You increase your transmitter power, you're only affecting the performance of your transmit signal. If you go to a better antenna with gain and a pattern, that's going to improve both transmit and receive. There's two different ways we lose power in the transmission line. One is called matched line loss, where if you have a 50 ohm transmitter, 50 ohm coax, and a 50 ohm antenna, which is the desire, the goal, you're still going to have some basic loss due to attenuation in the cable. Not all of the power from your transmitter will get to the antenna. But if there's an impedance mismatch between the feed line and the antenna at the far end, some of the power is reflected. We'll have a whole session on that. There's an added loss in the cable due to the reflected power. And we'll try to clear up a lot of those mysteries when we get there. So let's talk about transmit power. Just as I've already covered these things, but so we got our baseline reference is a transceiver running 100 watts. So we're defining that as 0 dB with respect to our power. We have a half-wave dipole, that's our reference antenna, 0 dB as far as comparing antennas are concerned one to another. We start with the dipole, our reference is 0. And I already mentioned that if you contact somebody and, for example, they tell you you're S7, all that means is at that moment in time, under whatever the conditions are over that particular path, your signal strength is S7, but it's going to constantly change probably. But we can make comparisons. Anyway, I thought you might find this interesting if you haven't been around a long time. It used to be that we were limited to 1,000 watts input power. Now, someone in the club asked me recently, what does input power mean? Well, in the old days, if you've got a power supply that puts 2,000 volts on the plate of your vacuum tube amplifier, and you tune the amplifier for 500 milliamps of plate current, which is half an amp. So you got 2,000 volts on the tube, and the current through the tube has been adjusted for half an amp. That's 1,000 watts input and the power supply, when you're not transmitting, will be typically a voltage higher than 2,000 volts. So when you actually transmit, it'll come down a little bit. So when you're transmitting, if it's 2,000 volts on the plate of the tube and 500 milliamps, that's 1,000 watts input. But circuits, these things are not 100% efficient. There's various classes of amplifiers. I just picked a number out of the air. It might be slightly high, but let's assume that we only get 70% of that power out to the antenna. So that's 700 watts. It might be 650. It could, anyway, I chose 700. So running by the old rules, legally, we're going to be limited. We were limited to like 700 watts output, give or take, okay? I don't remember the year, but they changed the rules to let us run 1,500 watts output. That's nice. They did us all a favor, because now to run 1,500 watts out, you're running probably in excess of 2,000 watts input in many cases. Well, if you compare 700 watts, which was our maximum output under the old rule, to 1,500 watts today, they just handed us a freebie of a 3.3 plus additional dB of transmit signal just by changing the rules. I've already covered this, but here's here's our base reference station, but now we've added the amplifier, the 1,500 watt amp into the picture. So we got 11.8 dB of gain, and I already mentioned that's basically roughly a 2S unit increase in your signal strength. Okay, so This is just more about dBs and trying to get comfortable with what power ratios, how that relates to decibels. So sort of in the center here, I have 100 watts compared to 200 watts compared to 100 watts, so I've got 3 dB gain. So going up the chart, every time I double the power, I get an extra 3 dB gain. You can see where I didn't double the power. There's the bottom line is every time you double the power, you can add another 3 dB. But going from 100 watts to 1500 watts is 11.8 dB. If I were to change my reference from 100 watts and start lowering it down to 50, that adds another 3 dB compared to 50. I can go all the way down to like QRP level, and you can see as we go down to the bottom of the chart, 1 watt compared to 1500 watts would be 31.8 dB of gain. Okay, let's talk about antennas. Old timers told me when I was a kid, antennas are part science, part art, and part black magic. Largely due to the fact that back in the in 1960, nobody really understood any of this stuff. So it was all magic. We know a lot more today about antenna theory than we did back then, but there's still some magic involved in, if you want to go that route. Okay, this is probably obvious, but the most important component of any station is the antenna. Hands down, no argument. If you're going to spend money, you should spend it on having as good an antenna as you can have, okay? You can go out and buy a $5,000 or a $10,000 radio. There are some that are that expensive. If you're willing to pay that money, bring it home, and the experience you have with that fantastic piece of technology is going to be limited by the antenna, okay? Now, antennas are reciprocal in that whatever improvement you get as far as gain or radiation pattern, that applies to both transmit and receive. And we're not here to spend all day talking about antennas, but I'll let it go at that. We are going to talk about forward gain today. We're not going to talk about front to back, front to rear, or front to side. We'll talk a little bit about height above ground. And when we get to SWR, we'll talk about feed point impedance and resonance, because that all factors into the big picture. Ground conductivity plays a role. I'm not going to get into that in this talk, other than maybe just mention it a little later. And obviously, you don't want your antennas can be affected. The radiation pattern and the efficiency, the performance can be affected by close by other antennas. They can interact, power lines, So you want to try to keep things as in the clear as possible. Now, just a couple things about resonant antennas. This might be slightly misplaced, but I'm going to bring it up now. A lot of people don't understand the significance of resonance. Resonance is all about impedance, not performance. A resonant antenna is one where the impedance of the antenna is purely resistive and has no reactance, either inductive or capacitive, okay? And resonance is no indicator of an antenna that's going to be a good performer. It's basically, they're two different issues, okay? So my point here, and somebody that I knew years ago coined this term, but a resonant antenna can work like an air-cooled dummy load. In other words, it's not an antenna at all. Just because it's a pure resistance impedance doesn't mean that the antenna itself is going to be performing well. You can have an antenna that's not resonant, that has a complex impedance made up of both resistance and either inductive or capacitive reactance, and that might be the most fantastic antenna you can imagine. I just want to make that point that resonance has to do with the impedance and not performance of the antenna. Okay. Now, there's something called an I say isotropic. I noticed Jim in his talk said isotropic. I come from Pennsylvania, Dutch Amish country. I don't know how to pronounce words. I couldn't pronounce coffee. I couldn't pronounce roof. Or, anyway, I say isotropic. Okay, now the little sphere there represents an isotropic source. What is that? This is a strictly theoretical thing that means something to mathematicians, for example. In theory, well, even in practice, an isotropic source is an infinitely small, if you can imagine, an infinitely small point source that radiates equally in all directions and all dimensions. So the radiation pattern, could we build such a thing, would be a sphere, okay? It's not possible to build one of these things unless some genius, anyway, it's not possible. This is strictly a mathematical starting point or reference point that we can then compare antennas with different patterns to determine gain compared to an isotropic source. Now, if you have looked at ads for antennas, antenna manufacturers will quote quite often two different gain numbers. One says dBi and one says dBd. dBi is gain of the antenna reference to an isotropic source. dBd is gain reference to a dipole. My opinion is that since we can't actually build an isotropic source, a more practical reference antenna is a dipole, which is a good antenna. It's simple to make, and so many manufacturers will quote both numbers, both isotropic and also the comparison to a dipole. Now, I'm told, I've never played with antenna modeling software, but in that theoretical world, if I can put it that way, everything's in isotropic, okay. But on a day-to-day thing for typical hams, the more meaningful thing to me is how does this compare to a dipole as opposed to an isotropic source? Now, what does gain in an antenna mean? We can increase our transmit power. We're actually adding real power into the system. But when it comes to gain with an antenna, we take the radiation pattern and we narrow down the pattern, focus the energy into a smaller space, so to speak, and we get the effect. The effect is as though we've added real power to the signal, but we do not add any actual new power. We're just getting the effect of additional power by the altering of the antenna pattern. The example that I like to use, there's several that you can use. I like the idea of the flashlight analogy. Imagine us being in a totally dark room, no light whatsoever. We take an old flashlight when the light bulbs used to be incandescent little round bulbs. Take the light bulb out of the flashlight, take the batteries out of the flashlight, connect the batteries to the bulb, stand in the middle of the room. Now that's not an isotropic source. There's a socket on one end of the bulb. I mean, you don't have an infinitely small point source radiating equally in all directions, but you're kind of trying to approximate an isotropic source. That set of batteries and that light bulb will provide very dim light in the room, okay? Now, let's take the same bulb and the same batteries, put them back in the flashlight where we have the reflector. It's the same power, it's the same batteries, but now all of a sudden we've taken what was a dimly lit room, and we've focused all that energy into a very, in some cases, narrow beam that's extremely bright, and in some cases so bright you don't even want to look at the flashlight directly. That's what we do with, effectively what we're doing with antennas by narrowing down the radiation pattern of the antenna. We're concentrating the available power from the transmitter into a more narrow area, And the effect of that is gain without actually adding any new power. I hope that makes sense. Let's talk about a dipole. Okay. A 40-meter half-wave dipole put up in horizontal fashion like this, strung between two supports. It's physically horizontal, but it's considered to be horizontal polarization because the way this is defined, horizontal versus vertical polarization, is the direction of the electric current is through the wire. The magnetic field is 90 degrees to that, okay? So if the electric field is traveling horizontal, that's horizontal polarization. If I take that and turn it into a vertical, I've got the same overall pattern, but now it's tipped up on its side, okay? So this pattern in the middle here, it looks like a donut, so we don't have a total sphere any longer. Mathematically, that represents 2.15 dB of gain over an isotropic source. Does that make sense? Everybody follow that? Okay. Now, if we were to cut the donut in half in the middle and look down at it from the top, what you see over here to the right is the radiation pattern in terms of azimuth. I guess that's the right word. The radiation pattern is broadside to the wire and not so much off the ends of the wire, okay? Now, this is not an accurate depiction because there's two perfect circles here. It's actually would look more like an actual number 8 turned on its side. It wouldn't be a perfect circle necessarily, but anyway. So a dipole mounted horizontally is considered horizontal polarization with this radiation pattern broadside to the wire. But now, if we look into the end of the wire, which is this bottom thing here, at the very bottom, if we look at the end of the wire, what this big diagram at the bottom is representing is the takeoff angle of the signal from the angle with respect to the ground, okay? And you can see, and I don't know at what height this diagram represents, but this is showing that the green line here is where the maximum energy is concentrated as far as the takeoff angle is concerned. Now, you'll see down here at the bottom, I guess I could stand up for a minute. Down here at the bottom, there's not so much energy at very low angles, which is extremely important for long distance communication. Now, if I lower the height of the antenna with respect to ground, this whole pattern is going to start looking more like a circle, a real circle. And this part here is going to go up, straight up. So if you want a near vertical incident skywave antenna, the closer you put it to the ground, the more energy is going to go more or less straight up so you can work closer in. Did I say that backwards? You want to get it closer to the ground. Now, if I raise this dipole antenna higher and higher off the ground, this takeoff angle is going to start to come down, and this is going to get compressed more downward. And so the energy will start to be concentrated at lower angles. And as far as half-wave dipoles are concerned, if you can get the antenna up a half wavelength, that's a really good antenna at that height. The problem is a half wavelength on 40 meters is roughly 66 feet. Most of us can't put a wire up 66 feet. But on 20 meters and higher, 20 meters, 33 feet is a half wavelength. Now, a dipole on 80 or 160, you'd have to go up 270 feet on 160 to be a half wavelength.
And that's why half-wave dipoles on 160 are worthless, except for NBIS operations.
That's true, except there are some anomalies in the propagation where people make long-distance contacts. But what you said is essentially correct. Most people on the lower bands use vertically polarized antennas to achieve the lower angle. Any questions on this? Let me move on here. Okay, so we've declared, and actually the radio world has declared in many cases, a half-wave dipole as our reference antenna. We can easily build one, and we can compare. We can put up a rotary dipole, for example, and a beam, and we can do real comparisons between the two. So the difference between a half-wave dipole in free space compared to an isotropic source is 2.15 dB. This third line there, I'm going to delay that. A half-wave dipole near the Earth has some additional gain that people don't normally talk about. And I'm going to postpone that a little bit. We'll get to that. But the half-wave dipole, I said this already, is a basic building block for many antennas. And of course, manufacturers competing with each other are always trying to brag about their gain figures. You go back decades, okay, we've learned a lot about antennas. So antennas, gain figures many years ago for beam antennas were quoted much higher than reality. Some of it was probably competition and false advertisement. Part of it was nobody really truly understood how some of this stuff worked. And so we have the two different ways that I mentioned. You can compare gain to an isotropic source or to a dipole. These gain figures have been so all over the place over the years that the ARRL many years ago came up with a policy that they refused to publish gain figures in their advertisements. So if you want to if you're an antenna company and you run an ad in QST, you're agreeing to abide by the fact that they won't publish your claimed gain figures in QST magazine. Okay? Now let's talk about high gain antennas. This is a picture of a high gain 4-element 20-meter monoband Yagi. I had one of these in the 70s. It was by far the best 20-meter antenna I've ever had in my life.
High gain's a brand name, not a...
Thank you. Yeah, High Gain is the name of a company. It's also an antenna with roughly 6 dB of gain. The amount of gain for a beam antenna is determined not only by the number of elements that you have, but by the boom length. The closer you have the elements spaced, the lower the gain. I'm just making generalizations here. So 4 elements on a relatively short boom will have less gain than 4 elements on a much longer boom, just so you kind of understand that. Every additional element that you add provides less and less additional gain. Okay, so I'm working with round numbers here. A 2-element beam, give or take, is about 4 dB of gain. Usually they're quoted at 4.1, 0.2, or 0.3, depending on how they're tuned, whether it's for gain or front to back. Some of them might be slightly under 4 dB. A 3-element beam is typically a little over 5 dB of gain. A 4-element beam is around 6. Oftentimes it's going to be less than 6 or a little more than 6 if you're really tweaking things. Okay, so each additional element gives you more gain. The longer the boom, the better. And you get the gain by focusing the energy into this narrow, or this much smaller area rather than spewing it out in all directions, okay? And you see this little tail back here, that has to do with the front to back ratio. So you can run a test with a guy, how loud are you when you're pointed at him, turn the antenna around and see how much lower your signal strength is. And that can be a relatively accurate measurement on your S meter. If the conditions are stable, you know what you are pointed at you and you know what you are pointed away. Again, it's a relative thing, but that becomes useful. Okay, there's something called effective radiated power. Excuse me if I slur some of my words. I try to slow down. The effectiveness of the total antenna system from the transmitter to the radiated signal is expressed as effective radiated power. So you take the transmitter power, or if you got an amplifier, the amplifier power, which is your transmit power. You identify all the losses in the system. The biggest one is probably going to be the transmission line, but insertion loss from things like tuners, SWR meters, coax switches, and on we can go. It's hard, by the way, to determine all those individual things. The big item is the transmission line and its loss. But the definition of effective radiated power is transmitter power minus the losses, and then add in the gain of the antenna. So you take the plus and minus numbers, add them, arrive at one final number, and that gives you your effective radiated power expressed in watts, okay? And there's something called effective radiated power compared to an isotropic source, and there's going to be a 2.15 dB difference there. Now, let's look at, on the left-hand side here, starting at the bottom is 100 watts and 0 dB. That's 100 watts into our reference dipole. And so ignoring transmission line losses, for the moment we're going to pretend there's no loss in the system. So ignoring losses, if I am running a 4-element beam, my 100 watt signal compared to a dipole on the 4-element beam is effectively going to be 400 watts. Okay, because it's every time you double the power, it's 3 dB, so you go from 100 to 400, you doubled it twice, and so you have a 6 dB gain. So if we go back to the top, 1500 watts compared to 100 watts is 11.8 dB of transmit power gain. And into a dipole with our reference with 0 dB, my effective radiated power is 1500 watts, using the dipole as our reference of 0. Now if I go to a 2-element beam with an additional, just use a whole number, 4 dB of gain, I've now got 3,765 watts of effective radiated power, and so on as you go to a 3 and to a 4-element beam. 1,500 watts of power into a 4-element beam is 6,000 watts effective radiated power, ignoring the fact there's loss, which I will add into the picture later. Okay? Everybody follow that? So I think that's kind of impressive that you can have something in the order of 6,000 watts effective radiated power, and we're not limited to that. I only went to a 4-element beam as my upper limit. There's gigantic antenna systems that have far greater gain than what I'm accounting for in this talk. Now let's talk about a vertical. Instead of a half-wave dipole, we basically have a quarter-wave vertical, which is half of a dipole standing up vertically. Half of the antenna, now on 40 meters, instead of a 66-foot long dipole, we have a roughly 30-foot high vertical, and the other half of the antenna is the ground. Okay. The feed point impedance of a vertical, well actually, I didn't say this earlier, a dipole, the feed point impedance of a half-wave dipole in free space is 72 ohms, give or take a little bit. A vertical half of a dipole, so to speak, is 36 ohms. But what's really important with verticals is half of the antenna is the ground, which is the blue horizontal line. I actually said dirt, okay? Because you're applying power to the vertical. The feed point is the bottom of the vertical, center conductor of the coax, and the shield goes to the ground. The equivalent circuit of what you have here is 2 resistors in series. The radiation resistance of the antenna the coax, this is a equivalent circuit. So the center, one side of the coax goes to the end of the antenna, which is 36 ohms or less. And then the second resistor is the ground resistance. I should have put a slide on here that shows that. The point is, where we live in this rocky soil, our ground resistance can be extremely high. Your power is going to divide between the 36 or 35 or whatever ohms of the vertical to however many ohms the ground resistance is. It's very possible, more than possible, likely, many people who have vertical antennas that don't understand the big picture and don't install them like they should be installed, you're literally going to lose more than half of your power. Literally gets burned up in the dirt, just to make a point, because your power is going to divide between the resistance of the ground. There's an electric field. There's an electric field between the vertical coming down to the ground, and that electric current has to travel back to the feed point to complete the circuit. Well, if it's just dirt there and you just have a ground rod here for lightning protection, that current has to travel back through dirt, which is a high resistance. It's going to burn up. It can burn up well in excess of 50% of your power. The point is, the reason we have what's called radial wires is to provide a better path back to the feed point to minimize loss. We'll do a whole talk in the future on verticals if you'd like. I don't have time to get into it. I did want to point out that the radials affect what we call the near field, but we have no control over the resistance of the soil away from the vertical. I'd like to get into that in more detail, but I don't have the time. Okay, now I found this interesting. I had never really thought about this in the past, but the radiation pattern for a quarter wave vertical looks like the same radiation pattern for a dipole, only it's turned on its side. Now, out in free space, far removed from ground, we don't have the reference to ground, so what does horizontal versus vertical mean out in free space? It's the same antenna pattern for a dipole as a vertical, only one with respect, when you come back to Earth, so to speak, the dipole is horizontally polarized, so the donut is oriented upright. The vertically polarized donut or antenna, it's on its side. It's still the same, essentially the same pattern. So theoretically in free space, I'm fudging things a little bit, but more or less the gain compared to an isotropic source for a half-wave dipole in free space or a quarter-wave vertical in free space, the pattern is the same, okay? The verticals provide us with typically a lower angle of radiation than a dipole. That's illustrated, try to illustrate that with the takeoff angle over here in the lower right corner. I'm willing to do a talk on verticals if you'd like to get into this in detail. Okay, the top graph here compares a quarter-wave vertical in blue to a half-wave vertical in green to a 5/8 wave vertical in red. And what that shows you is that 5/8 wave verticals have some benefit. For example, at low angles, they're better performers perhaps. But there's lots of other issues we'd have to get into in terms of impedance. Quarter wave vertical being 36 ohms plus the ground loss makes a pretty nice, easy match to a 50 ohm coax in most cases. Some of these other verticals, you've got very high impedances and you have to do impedance matching. Okay, theoretically, a quarter wave vertical is about 2.15 dBi. In practice, it's going to be less. A quarter wave vertical is going to be less than 0 dB, less than the performance of a dipole, okay, for various reasons. Now, because I think it's it's probably safe to say that the majority of verticals that are installed by hams are extremely inefficient. And so I'm not going out on a limb. There's lots to back this up. A vertical, a quarter-wave vertical that's not installed properly, if we were to define what proper means, it could easily burn up, lose, it could be less than 50% efficient. Now, I know you're thinking about a vertical, don't let that scare you away, okay? But if you have 1,000 watts out, you're going to lose over 500 watts in losses if you don't have the proper ground plane or ground system. Okay, now I want to tell you a story here that I think is very important. Years ago, when guys went on expeditions to various rare countries or islands, they would go to the trouble to transport 10-foot or 8-foot tower sections and beam antennas so they could set up a antenna with gain, even if it was only 25 or 30 feet off the ground. They felt that was the best antenna they could have to get the best results on the DXpedition. Mr. Schiller from Force 12, he and a team of people back about 25 years ago did an expedition from the Caribbean using entirely vertical antennas and near salt water, okay? Salt water is very highly conductive compared to dirt, okay? I'll make this short. They set new world records in the DX contest using all vertical antennas because the vertical antenna traveling over salt water, the losses were incredibly low, and the path over water, the signal at the far end is going to be incredibly loud. They made such an impression and proved that verticals by salt water were so fantastic that the major DXpeditions now, if they're going to an island, they take all vertical antennas. They don't transport tower sections and beams. Now, this is a statement that Tom Schiller made. You can choose to believe it or not. But they have determined, and I believe because they set new world records and have really set the world turned the world upside down, their claim is that a quarter-wave vertical over salt water will outperform a beam antenna at any height above the water. That's a little bit tough to imagine. But they set the new records. Okay, I find that interesting. Now, I choose my words in the title of this slide to try to wake people up, and I'm saying there's some hidden gain built into a horizontal antenna. It's a real gain that people don't usually talk about, but I kind of made this up. It's seemingly imaginary because it's sort of mysterious. People don't ever talk about it or think about it, although antenna companies are starting to mention it. Okay, now what this means is, we talked about an isotropic source out in free space. What that means is you're far removed from Earth, from the surface of the Earth. One book I read said, instead of free space, it said outer space, which I kind of got it. I guess that's true. The point is, the patterns, the isotropic pattern and comparing antenna patterns to an isotropic source in free space is all about keeping the antenna far removed from the surface of the Earth, which is going to alter the pattern of the antenna. So you might make an argument that there's some distance in terms of many wavelengths above Earth where you're far enough removed from ground to not alter the pattern. I think just in general, we just say, okay, this is out in free space, far enough away that the Earth isn't going to affect. So a horizontal dipole, and therefore other horizontal antennas like beams, benefit from what I call this hidden gain. So our reference dipole is considered to be 0 dB gain, but it has this hidden gain built into it. And this hidden gain, as you're going to see in a minute, is due to what's called ground reflection gain. Okay? But by making the dipole our reference antenna, we can compare the gain of other antennas to the dipole. Both antennas are benefiting from this hidden gain. We can say the dipole is our 0 dB reference, and our beam is 4, 5, 6 or more dB better than the dipole. But guess what? The performance of both of these antennas is better than those numbers because of this ground reflection gain. Okay? Does that make any sense? I don't know if I... So a 4-element beam was 6 dB gain over a dipole at the same height as the dipole. It's 60, a 4-element beam at the same height as our reference dipole is 6 dB, the performance is 6 dB better than the dipole, but the performance of both of those antennas is actually better than we realize because of this hidden gain. So I guess what I'm trying to say in different words is that there's more, the reference dipole of 0 dB has as much as 6 extra dB built into that reference, which applies to the other antennas. So what is ground reflection gain? If you imagine this free space donut pattern for a dipole, when you bring it down close to Earth, I've erased the bottom half of the donut to try to show you that as you approach close to Earth, the radiation going down is reflected back up. And theoretically, you've got a 3 dB gain just by cutting the, taking the total radiation going up and down, but reflecting the bottom half up, and you get 3 dB gain, theoretically. Now, in actual practice, the ground reflection gain is influenced by the height above ground. It can be as low, according to the books, the ground reflection gain can be as low as like 3.5 dB up to a maximum of 6 dB or so. And it has to do with, in this lower diagram here, if the antenna is your beam or your dipole, with horizontal polarization, you've got direct radiation going straight up into the ionosphere. But you also got, you've got energy in this circle. You've got energy going down at some angle that is going to get reflected back up. So at some angles, the reflected wave is going to be in phase with the direct wave, and they add together and effectively give you as much as 6 dB of gain. Does that make sense?
But that's a perfect world.
Pardon?
That would be a perfect world where they reinforced each other.
Right, there's going to be other parts of that picture where that it cancels, okay? So it's not like you're getting 6 dB gain at all angles,
Well, there's no perfect round here.
Okay. But the whole point of this is that we talk about antenna radiation patterns in free space and gain figures in free space. Once you come down to the real world here close to the Earth, the signals get reflected and alters this in terms of both pattern and gain. Okay, one thing I've observed for many years is I've had a beam at 65 feet, 3-element beam, and I have a high gain high tower vertical, and I can switch on 20 meters back and forth between the beam and the vertical, and across the board the difference is at least 15 dB stronger signals on the beam compared to the vertical. Sometimes it's 20 dB. That's a huge difference between the vertical and the beam. And I've always wondered, I wonder why that difference is so great. So here's some possibilities. I'm not saying this is 100% correct. But if I've got a 3-element beam and it's free space gain is, well, its gain is 5 dB over a dipole. But I've also got 6 dB of ground reflection loss. That's actually 11 dB. It's not, okay, we're still with me on this ground reflection gain. Okay, a vertical, now my vertical works pretty well because I got 100 radials. But if you've got a vertical that's losing half your power, 3 dB, just on the surface, 5 dB gain plus ground reflection gain of 6 minus 3 dB of vertical, right there is a 14 dB difference. Now, I'm not accounting for everything involved here, but
traps to go through though, too.
well, at the bottom here, my antenna is trapless, no traps. But many people have trap verticals which are shorter than they would be if they were full size, and you have traps in there which produces some loss. I'm going to defer to Mr. Schiller. He says that a trapped multi-band vertical antenna that's not installed with a really good ground system can be 20 decibels down. And I believe that. Okay? Wow. That is huge. So I can tell you from life's experience, I've been able to have a beam and a vertical for a long time. There is one huge difference between switching between the vertical and the beam. All right, I think we're doing okay on time. I think I can about get where I want to be, and then we'll quit and come back later for SWR. Transmission line. Coax cable came into widespread use following World War II. It's really neat from the standpoint that it's flexible, it's easy to work with. You can tape it to metal and it doesn't get all screwed up like 300 ohm twin lead. If you remember the old days with TV, you taped 300 ohm twin lead to a metal mast, it screwed everything up. So we've been using coax since World War II. You can get it in different impedances. Ham radio is pretty much standardized on 50 ohms, but there are situations where we can all make use of 75 ohm. 75 ohm is what the broadcast industry standardized. And so my receive antennas at home use, this is RG6, I use 75 ohm coax on my receive antennas. Now, the feed line is a really important part of our system, and we need to take a little time and talk about this, and then we'll be done for the day once we get through this. Manufacturers specify for each type of coax that they manufacture the loss in decibels for 100 foot of cable. That's called matched line loss. It assumes that you have a 50 ohm transmitter, a 50 ohm coax cable, and a 50 ohm antenna, properly matched, no mismatch, no standing wave ratio. Everything's working just the way it should be, but there's going to be a fixed amount of loss between the transmitter and the antenna, and everybody's manufacturer specifies that loss in decibels or fractions of the decibel. Now, where does that loss come from? There's basically two things that contribute to the loss. One is called ohmic loss or I squared R loss, which has to do with current traveling through this wire center conductor. The center conductor has a certain amount of resistance, current through and it's a copper wire is a very, very small fraction of an ohm per foot. Nevertheless, current through that resistance is going to get converted to heat that you won't feel or measure. There's going to be some loss in the wire due to current, I squared R, which represents power. I squared current times resistance, you get some loss. The other source of loss has to do with the voltage that exists between the center conductor and the inside surface of the shield. Not the outside surface, the inside surface. The signal that we transmit and receive is confined to the inside of the surface of between the inside surface of the shield and the center conductor. It doesn't travel on the outside. There's some exceptions. We may not get to that, but so when it comes to the voltage between the center conductor and the shield, there's some leakage or loss as a result of that voltage. So there's different dielectric material that you can have in here. You've heard of the term foam coax? Okay, it turns out, I'm getting ahead of myself, the best insulator or the best dielectric between the center conductor and the shield would be air. And that would be open wire line. I'll get to that in a minute. So if you have foam coax, my understanding is the foam has got a lot of air bubbles in it, which helps a little bit to lower the loss in the feed line, okay? This is LMR 600 cable. I use this to go 330 feet from my radio to the feed point on my beam back in my woods. I would have too much loss if I didn't go to a bigger coax. Now this is LMR 400, which I also use, okay? You can see that the spacing between the center conductor and the shield is less, so there's going to be more loss. The center conductor is a smaller diameter copper wire. The point I want to make, and this is LMR 600, LMR 400. Jim brought in some really teeny little cables. What did you say these, RG what? RG 213. Generally speaking, this is RG 400. It's safe to say in general terms, the larger the diameter of the coax, the larger the spacing between the center conductor and the shield, and the larger the diameter of the center conductor, the lower the loss, okay? Now, before coax, people oftentimes use something called open wire line. Now, I have two bidirectional beverage receive antennas, and I made them out of galvanized fence wire, electric fence wire, and I made 1,000 of these insulators in my friend's shop in his garage. So I have two 400-foot long beverage receive antennas at right angles that I can cover all four major directions. So this makes up my two-wire beverage antenna, but it's also a representation of actual open wire line. If you had 600 ohm open wire line, although I've never had any of that, I've been told that that's something as much as 6 inches separation between the two wires. Since this is all air, the loss due to the dielectric in here is way, 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 way down, okay? So you'll learn, if you come to the next SWR talk, it's really the loss, the attenuation in the feed line that is a problem at higher SWR. But this is, if you were to use open wire line to like a loop antenna, which you'll be able with the tuner to use that loop on all the different bands or most of the different bands. The impedances are going to be vastly different from one band to the other. You're going to have extremely high SWR on this open wire line, but if the tuner can handle the mismatch and tune it okay, your losses due to the high SWR will be very low because of very low loss in the open wire line. We're going to cover that in the part 2 of the talk. So we got open wire line on one end. We almost all use coax these days. Generally, the bigger, thicker, larger diameter, the better, the more expensive. This is RG 400. This has more loss, obviously, than this, but it's used by our top-tier competitive stations because this has extremely good shielding, very little leakage. And if you're a multi-contest station running 5 or 6 stations, one on each band, 24 hours a day for the weekend, any leakage between stations can cause you all kinds of grief. That's why they have bandpass filter. I'm getting into stuff I didn't mean to get into. This is excellent. This coax costs over $5 a foot. These are very convenient for all your patch cables between equipment. So a lot of these guys, all their cables are this kind of stuff as opposed to this less flexible stuff. Okay, a piece of transmission line, a piece of coax acts as an impedance transformer. So if I have an antenna on this end of the coax and its impedance is vastly, it's not 50 ohms, for example, it's some other impedance that includes either inductive or capacitive reactance, the transmission line is going to transform that impedance so that your transmitter or your antenna tuner on this end is going to see an impedance that's different from this impedance on the antenna end, okay? Just want you to be aware of that. We'll deal with that more when we get to SWR. There's something called velocity factor. We know that electromagnetic wave travels through free space at essentially the speed of light. It, however, does not travel at that speed through wire or through cable. It travels at a slower speed. One of the specs that manufacturers will specify for each coax is something called the velocity factor. Many of the velocity factors are 85%, 87%, even as low as 66%, which means that the signal is going to travel through the cable at 66% of the speed of light. We don't care. You're going to hear the difference. But where the difference comes in, because of the way the impedance transformation works, if you wanted to cut a piece of coax to be a half wavelength long at a particular frequency, well, a half wavelength in free space is one distance, but because the signal travels slower in the cable, you have to take whatever the free space wavelength is in feet and inches, for example, and cut the coax to be 66 or 85% of that, because that's the speed at which it's going to travel through. Does that make sense? Okay. There are places where this, normally day in and day out, we don't care about that, but there are things like phasing of antennas where you need to, if you're using coax, you have to understand all this stuff to cut things to the right length. If you want a piece of, the impedance at the antenna will repeat itself every half wavelength. So if you've got an extremely long piece of transmission line, every half wavelength, you'll see the same impedance that exists at this end of where the antenna is. I'm going to let that go at that. We'll come back to that. Each foot of coax has a certain amount of capacitance. So if you're working with an antenna like, let's say you have an inverted L antenna, which you may not know what that is, but you make it long enough to where it's inductive. It's a little bit longer than it should be, so it has inductive reactance. If you can make an inverted L antenna a little bit longer than a quarter wavelength in order to get the resistive component of the antenna up to 50 ohms. But because you made the inverted L longer than it would normally need to be to get the 50 ohms, you now have introduced inductive reactance into that antenna. So you can actually determine the inductive reactance and come up with a capacitor of the opposite equal but opposite reactance, and cut a piece of coax to that length and actually use a length of coax coiled up as a capacitor. I've done that in past years. I don't know if I explained that right, but let me move on. We talked about open wire lines, so this is a picture of hard line. This is just half-inch hard line. You can see it's a pretty big center conductor, but the shield is a rigid, solid copper, basically. So you can't bend it real easy. So as we already discussed, the bigger the cable, the less loss. Okay. We'll have you out of here at 12. Hope that works for you. We're almost there. So It's been taught down through the ages. I was taught this in school. It's taught in the textbooks that maximum efficiency when it comes to transferring energy between circuits or networks occurs when the impedance are matched. I don't think there's any argument there. Someone recently said that wasn't the case. I'm going to ignore that for the time being. So in ham radio, we have solid state radios designed for 50 ohms. We have 50 ohm coax. And ideally, we would like an antenna that has a feed point impedance of 50 ohms. We'll talk more about that later. If, in fact, we had this perfect world where everything is properly matched, the standing wave ratio is called 1:1, and there would be no reflected power coming back towards the radio from the antenna. Okay? So a 1:1 SWR is often referred to as being flat, and it's something that everybody has been misled or brainwashed or convinced to believe that we have to do everything in our power to achieve a 1:1 SWR, but it's seldom possible. And we'll get into all of that in part 2 of this talk. Now I have here a 50 ohm dummy load. I think we're close enough to the end for today that I can take the time to do this. Whoops, I had it the right way the first time. Anybody here, is there any, well, I don't like to ask questions and put people on the spot. Let me just say that some of you may not have actually seen what a 1:1 SWR looks like on a meter, on an analyzer, and why they call it flat. Okay, now I can walk around here. This is an amazing piece of equipment. You know, 50 years ago, I don't think anybody would imagine we'd have stuff like this. So I'm going to set this up for essentially 10 meters. I'm going to put it at 29 megahertz. 10 meters is 28 to 29.7. I'm going to scan the frequency from 27 to 31 megahertz, which includes all of 10 meters. This is a non-inductive, purely resistive 50 ohm dummy load. So I've got it set up to do that scan. And now I'll walk around so you can see that. See, that's plotting the SWR. It's a flat line at pretty close to 1:1. Everybody, you understand?
I've got one.
You know what this is like.
And I
Okay.
saw it at the house when you were.
Okay.
Can you show it to the camera?
Oh, sure. This is a 1:1 SWR.
It's flat.
It's flat. But guess what? You can have a flat SWR on an antenna. It just might be 15:1 SWR. I saw one of those recently.
My house.
When we get to SWR, we'll come back to this because we're going to talk about all kinds of impedance things and mismatches and so on. Okay, so I will tell you that I was one that was taught from day one. Once I knew that there was something called an SWR, I was taught that you got to have zero reflected power at all costs. Anything above zero reflected power and you got a problem. That is not true. It can be in certain circumstances. This represents, well, this I took directly from Times Microwave, who makes these LMR and LMR 600 coax. This shows what's called the matched line loss per 100 feet of cable, in this case for LMR 400. And perhaps I need to stand up for this. I find it interesting that the attenuation here in decibels per 100 feet comes down to 30 megahertz, which is the top end of HF radio, and stops there and doesn't continue. I added this line with this arrow here because what I wanted to show you is At 30 megahertz, which is actually a little past the top end of our 10-meter band, the loss for 100 feet of this cable is 7/10 of a decibel. Okay, but this is 30 megahertz, 20 megahertz, 10 megahertz. They don't even bother to go below 10 megahertz. But in reality, this loss continues to go down, so that on the very low end of HF radio, the loss per 100 feet of cable, the attenuation, is a very tiny fraction of 1 decibel, and we'll go through all of that in the part 2 of the talk. Okay, I want to tell you that if you a coax like LMR 400 or some of its competing versions of RG8 and so on, the loss is considered low enough that we're in pretty good shape anywhere from the low end of HF to up to 30 megahertz if we're dealing with 100 feet or less of cable. Now, if you're blessed with acreage and your antennas are hundreds of feet away, then you got to multiply these numbers by add it up for each 100 feet. That's why I got larger cable, more expensive cable, to go 330 feet to my beam. So generally speaking, just about any RG8 type coax that you can buy, this is a sort of a version of that, they're all going to be within 1/10 of a dB or of each other on these frequencies. And under reasonable situations, I'm going to say even, I'll show you this in part 2, even at 10 meters with a 3-to-1 SWR, the loss on this cable is tolerable. Okay, I'll let it go at that for now. So where am I at here? Okay, this is an illustration of LMR 400 coax running 100 watts from the transmitter into 100 feet of this cable, okay, under matched conditions. So 100 watts into a 50 ohm coax and a 50 ohm antenna. And at the top that says, if we go to 440 megahertz, which is actually a UHF band, only 54 plus watts of that 100 watts is going to arrive at the antenna due to the loss in the cable. As we go down in frequency, things get better. So at 2 meters, we're up to almost 71 watts. Again, this is under perfect matched conditions, no standing wave, no reflected power. 6 meters, we're up to basically 82 watts. Well, at 10 meters, the loss is only at 28.5 megahertz. The loss per 100 feet is down to 0.65 dB. That translates into 86 watts out of the 100 is arriving at the antenna. That's not bad. That's pretty good. Now go down all the way to near the bottom to 160 meters, and over 96 watts out of 100 is going to arrive at the antenna. Okay, I just wanted to illustrate that. This is under the conditions we would like to have, matched impedances across the board. Now, at the very bottom is 600 ohm open wire line, which would be spaced about 6 inches. This is only 2 inches. Comparing that to LMR 400 at 28.5 megahertz, open wire line is going to give you over 97 watts at the antenna compared to 86 watts with the LMR 400. You can decide for yourself, you know, how much money you want to spend on transmission line and where it makes a difference in your performance. Part 2 on SWR, we'll get into this in much more detail. That talk should take less time. I'm guessing we can get through all of part 2 in 2 hours instead of almost 3. Okay, I know we've been here a while. Let me show you something really neat. This is a really neat tool, and if you get the paperwork that goes with the talk, this website is listed. Okay. this is available on the internet from a guy in Cuba. It's called the CO8TW. And what you can do here, he's listed all these different feed lines up here at the top. You can select what feed line you're interested in working with. Like I have LMR 400, and I can set the line length to 100 feet and 10 megahertz, and my SWR is 1:1, and then I can hit calculate, and it's going to tell me that over 91 watts of my 100 watts will arrive at the antenna using LMR 400 on 30 meters, 10 megahertz. So you can sit here and you can plug numbers in, like if you got a couple of 100-foot long run, you can specify that length, and you can get familiar with how the losses work with different feed lines when you have a matched condition, a 1:1 SWR. I'll just show you this now, but we'll spend time at this in part 2. So on 100 feet of cable, LMR 400 on 30 meters, 10 megahertz with a 1:1 SWR, over 91 watts makes it to the antenna. Okay, let's change that to let's just go big. Let's change it to a 5:1 SWR. Heaven forbid anybody would try to use an antenna with a 5. Anyway, that's we've all been conditioned to think, 5:1 is terrible. Okay, so let's hit calculate. Now we had almost 91, we had 91.5 watts, bingo. Even with a 5:1 SWR, I'm getting 81 watts. If your tuner can handle it, I mean, you're not blown out of the water performance-wise, And we're going to play with this tool in the second part of the talk. Okay, let me go back to, I think we're done, but we're almost done. Okay, a couple more slides and we're out of here. I wanted to make a point here that you might not have thought about. But if I have a 100 watt transceiver and I switch on a 1500 watt amp, we've seen previously that that's an 11.8 dB gain over 100 watts. But if I've got a transmission line that has 3 dB of loss, I just pulled this out of the air for a convenient number. If I have 3 dB of loss in the transmission line, that 1500 watts is going to be cut down to 750 watts at the antenna. If I'm running 100 watts, it's going to be cut down to 50 watts at the antenna. But notice something real interesting here. The ratio between 750 and 50 is the same ratio as 1500 to 10. Okay, so either way, I've got an 11.8 dB gain. However, I lost half my power in the coax, so I'm actually 3 decibels down in both cases from where I started. Did I say that right? Anyway, does that make sense? So if I've got a lossy transmission line and I lose half my power, and I'm running 100 watts, so I'm going to lose half of it, but now the guy says, I don't hear you very well, and I switch on my amp, I still got 3 dB loss, but I'm still the same ratio as far as power increase. I still get my 11.8 dB gain over the transceiver, but we're down by 3 dB. Okay. All right. I think, 2 slides and we're done. Okay, so what we have here is, in addition to this, you saw this view graph before talking about power, gain, and antenna gain. What I've added to this is in the red, and it's just one example. So the red indicates I've now, previously we assumed 0 loss in the system, transmission line wise. Now I'm adding in 0.65 dB of loss in the cable at 10 meters, under a matched line condition, no SWR. And so what you can see in red here is that my 1500 watts into a dipole, my effective radiated power has dropped from 1500 to 1291. If I come down here to near the bottom, if I've got 1500 watts into a 4-element beam, which is 6 dB of gain, my effective radiated power dropped from 6,000 to 5,166. And the very bottom is 100 watts into a dipole. I'm down to 86. With loss, I'm down to 86 watts with that loss at 10 meters. These are approximate numbers, by the way, depending on the, I did some rounding in a few cases. I used some whole numbers rather than the pluses. If you try to reproduce these numbers, you should get very close to these numbers, but they're not precision numbers. You may be off a bit, but this gives you a relative sense of the impact of the loss at 10 meters. If we took the time to look at the lower frequency bands, the impact is less and less due to less loss. So this is our summary. We could improve our performance in terms of our transmit signal compared to 100 watts by going to an amplifier, and if you go all the way to a 1500 watt amp, you can get 11.8 dB a gain, maybe as much, roughly 2S unit improvement. Okay, gain with respect to an antenna, we declared a dipole as our reference of 0 dB, so you can just go from 2 to 3 to 4-element beams and see the improvement. And of course, we left out the monster antenna systems that some people have that are far greater than 6 dB of gain. And for the moment, at HF using reasonably good coax, I'm listing the loss in the coax under matched conditions as something under a decibel, okay? But we're going to explore all this loss stuff in much more detail, but in practical terms, when we do part 2 on SWR. That's it. If you want, I'll just press the button a bunch of times and you can kind of see what you're going to get if you come back for part 2. I'll just run through this. By the way, I'll tell you, that's the first SWR meter I ever saw. Well, the president of my hometown club showed up with one in around 1964, and we all oohed and awed, what is that? That was a Heathkit SWR bridge. We're going to go on the internet to some animation. We're going to look at moving waveforms and what standing wave is. We're going to do a couple versions of that. I'm going to tell you about a 428-page book by Maxwell, what he teaches, which is primarily true, but some people don't like to agree with him entirely. And we'll talk about those differences. So we'll start fresh. Those of you that choose to come back for part 2 will probably be able to do SWR in considerably less time than we spent here this morning. All right, I guess we're done.
Thanks, Ron.
You're welcome.